It's looking at this, well, pretty mind-bending idea,
Mm-hmm.
creating a material that's like artificially super dense and specifically engineered to interact with particles that normally just phase right through everything,
Yeah.
like neutrinos.
Yeah, it's a concept that really pushes the limits, doesn't it? It's sitting right at the intersection of advanced materials, particle physics, and even nanoscale engineering.
Definitely. A real thought experiment.
For sure. How do you even begin to detect something so incredibly elusive?
Exactly. So our mission for this deep dive, based on the sources you shared, is to really unpack this. We'll look at the core science, the structure they're proposing.
Right.
Consider the potential upsides, if it could even work, and then crucially really face up to the absolutely massive challenges involved.
Monumental is probably the right word.
Yeah. It's a wild idea, and we're hoping to, guide you through it.
Sounds good.
So let's jump in. The basic proposal in the sources.
Yeah.
It's all about layering, isn't it? Can you maybe walk us through that core concept?
Sure. So the fundamental idea, geometrically speaking, is actually quite clever. You'd be building this material from incredibly thin layers, like maybe even atom-thin layers, of some specially chosen substance.
Okay.
But the key isn't just stacking them like pancakes, one directly on top of the other.
Right.
The idea is to precisely stagger or offset each layer as you build it up in 3-dimension.
Okay, so like shifting each pancake slightly over from the one below it
Yeah.
in all directions.
That's a decent way to picture the staggering, yeah.
Oh.
And the whole point of doing that, this offsetting, is so that no matter which direction a particle, like a neutrino, comes flying through, its path is statistically, like, almost guaranteed to actually pass through the atoms of one of those layers.
Okay, so from the particle's viewpoint, there are no clear shots between the layers. It basically has to hit material somewhere.
Exactly that. You're geometrically arranging it to eliminate those potential gaps that a particle might find in a normal material structure. The sources call this making the material superdense, but specifically in terms of its interaction cross-section.
Interaction cross-section, like the target area.
Yeah, think of it like the effective target area each atom presents for an interaction. This geometry aims to maximize the total target area you encounter within a certain volume.
Got it. So the structure forces it to hit a layer, and the sources also mentioned packing these layers super close together, right? That's part of it too, for physical density.
Right, exactly. That's the other side of it. You get high physical density in the traditional sense, too, by squashing those layers incredibly close. So you're attacking the problem on two fronts, maximizing the chance of an encounter through geometry and maximizing the amount of stuff it encounters per unit volume through close packing.
Okay, makes sense. Now, why the big focus on neutrinos? We know they're famously hard to catch. What makes them such a particular challenge?
Well, neutrinos are fundamental particles, yeah, but they interact mainly through the weak nuclear force.
Right, one of the four forces, but weak.
Incredibly weak, yeah, especially compared to something like electromagnetism. At the distances involved in particle interactions, it's just feeble. Plus, neutrinos have no electric charge and almost no mass. Tiny, tiny mass.
So, no charge, hardly any mass, only talks via this super weak force. They just don't feel normal matter much at all.
Precisely. They just, zip right through. Billions, trillions from the sun are going through us right now, through the whole Earth, actually.
And we don't notice a thing.
Not a thing.
Yeah.
They can pass through light years of lead without a guaranteed interaction. That's why detection is so ridiculously hard.
Wow. Light years of lead.
Yeah. So this engineered material concept is trying to fight back against that low probability. It's trying to create a medium where you provide so many potential interaction chances, packed so closely, that you boost the odds within a, hopefully more manageable volume.
Right. Boost the odds per cubic meter, essentially.
Using a material that's also ideally optimized for those rare interactions when they do happen.
Okay, so if, and it's a big if,
Right.
but if we can make this layered structure with the right stuff, what are the advantages the sources talk about?
Well, the first big one, we've kind of covered the maximized geometric cross-section.
Right, making sure it hits something.
Ensuring the path intersects a layer, yeah. But then, okay, it hits a layer. You still need to maximize the chance of an actual interaction happening within that layer.
Okay. That's where the material choice comes in.
Exactly. And the sources are pretty clear on preferring high Z elements.
High Z. What's the Z stand for?
Z is the atomic number, so number of protons in the nucleus. High Z means elements with lots of protons and usually lots of neutrons too. We call protons and neutrons and nucleons collectively.
Okay, so heavy elements basically, like lead.
Lead, tungsten, The sources even float the idea of hypothetical super heavy elements if they could be made stable.
On why heavy? More stuff in the nucleus means.
It generally means a larger interaction cross-section for neutrinos. More protons and neutrons just give the neutrino more potential targets to interact with via that weak force. It's like having a bigger dartboard, statistically speaking.
Makes sense.
You also want high nucleon density overall, just packing as many protons and neutrons into a given space as possible. And while neutrinos mostly interact with nuclei, they can also scatter off electrons. So having a high density of easily accessible electrons is also considered a plus.
So pick heavy stuff, pack it tight. Got it. What other potential benefits did the sources mention?
Well, there's the idea of tunable properties. You've got the high physical density from packing layers close, but maybe you could also fine-tune the thickness of each layer, or even use specific isotopes of an element.
Isotopes. Same element, different number of neutrons.
Right. Some isotopes might just happen to have slightly better interaction characteristics, or perhaps they produce a cleaner signal, a secondary signal, when an interaction actually happens.
Which leads to that other point, right? Integrated detection.
Exactly. The dream version of this material wouldn't just be the target, it would be part of the detector itself. It could be, for instance, a scintillator.
A scintillator. That's something that flashes light when hit.
Yeah, when an energetic particle goes through it, like the particles produced after a neutrino interacts, it emits a tiny flash of light. Or maybe the material could directly produce other signals, like Cherenkov light.
Cherenkov light.
Yeah.
Oh, that's the blue glow
Yeah.
from particles going faster than light in water.
Faster than light in that medium, yeah. Or maybe it could show ionization trails, like little tracks left by charged particles. If the material itself signals the interaction, well, that makes building the overall detector much simpler.
Okay, yeah, that paints a really cool picture, a self-detecting super target material. But the sources are just as strong on the challenges, aren't they? Calling them monumental. Where does the difficulty really start?
The absolute brick wall, the fundamental problem, is still just how incredibly weak the neutrino interaction is. Even if you nail the material science, you get your high Z elements, you pack them dense, you do the perfect geometric layering, the basic intrinsic probability of any single neutrino actually bothering to interact with any single nucleus or electron it passes, it's still just vanishingly small.
So even hitting a perfect layer of the perfect stuff still probably just sails right through.
Overwhelmingly likely, yes. It's a tiny, tiny chance per encounter. And what that means is, to get a high probability of an interaction happening somewhere in your structure, the total number of layers, the total path length the neutrino has to travel through this stuff, it would still need to be immense.
How immense.
The sources use phrases like, well, potentially astrophysical scales.
Astrophysical, you mean like planet size, star size. That's a bit beyond current tech.
Just a bit, yeah. And that leads right into the next set of massive challenges, actually making this material and achieving that super density on any kind of practical scale.
Yeah, I was wondering about that. Can we even make layers like that?
Well, that's a huge material science question mark. First, you need to find or, synthesize a material that has everything. High Z, high density, maybe scintillates, and critically can form stable, ultra-thin, maybe even single atom thick layers that you can manipulate.
That sounds like a miracle material.
Pretty much. And the sources point out many of the materials we like for high Z and density, like lead or tungsten, they don't naturally form nice flat layers like, say, graphene does. They're not lamellar.
So the best stuff for interacting doesn't like forming the structure we need.
That's a major hurdle, yeah. And let's say, okay, somehow you make these perfect layers. Then you have to stack them packed incredibly close, maybe just atoms apart while managing all the tiny forces between them.
Forces between layers.
Yeah, things like van der Waals forces, electrostatic forces, keeping trillions of layers perfectly aligned in 3D with that precise offset while these forces are trying to pull them together or push them apart. It's mind-bogglingly complex, way beyond what we can currently engineer.
Van der Waals. Those are the weak attractions, right? But over trillions of layers.
They add up, and maintaining subatomic precision over potentially huge volumes. It's just...
Wow. And the sheer number of layers required.
Yeah.
You said astronomical.
Yeah, the engineering scale is almost unthinkable. To get enough target atoms, enough nucleons to compete with current detectors, which are already kiloton scale, thousands of tons.
Right.
You'd likely need trillions upon trillions of these specialized layers, aligning them all with atomic precision, maintaining structural integrity. It's a level of construction of nanoscale assembly on a macro scale that is just science fiction at this point.
So materials we can't really make in the right form, structures we can't really assemble with the needed precision, at scales that are maybe impossibly large, it really hammers home the difficulty.
It does.
And just to be clear, when we say a neutrino interacts, what actually happens? It doesn't just bounce off, right?
No. An interaction is a fundamental process. The neutrino exchanges a force carrier particle via the weak force with a particle in the nucleus or an electron. This typically transforms the neutrino and produces other detectable particles. The whole point of the engineered material is to provide lots of good targets, like heavy nuclei and electrons, to make these rare events happen more often in a given volume, and ideally make those resulting particles easier to spot.
Okay. This whole approach feels completely different from how we actually look for neutrinos now. How do current detectors work in contrast?
Yeah, it's a totally different philosophy. Current detectors basically go for brute force. They don't try to engineer the interaction probability per atom through fancy structures. They just use absolutely massive volumes, kilotons, like we said, of relatively ordinary, cheap material.
Like water.
Ultra-pure water is a big one, yeah. Or huge tanks of liquid scintillator, sometimes lead, or giant chambers of liquid argon.
Okay, so they're not trying to force every neutrino to hit something special. They just put up a huge amount of regular stuff, hoping some will interact by chance.
Exactly. They accept the incredibly low chance per atom, but they compensate by having an absolutely enormous number of atoms in the detector's path. Out of the trillions and trillions of neutrinos flying through, statistically, a few will interact just by chance. And then the challenge is detecting the incredibly faint signals like those flashes of light from those very few interactions within that huge volume.
So this concept tries to boost the rate of interaction per volume, while current detectors boost the total number of chances through sheer size.
That's a good way to put it.
Okay, so let's try and wrap this up. This deep dive, looking at the source material, it's laid out this really sophisticated idea, hasn't it?
Definitely. A conceptual framework using these precisely staggered ultra-thin layers of some optimized, maybe high-Z material, all designed to maximize the chance a neutrino interacts.
Right, by creating this super dense medium, both geometrically forcing a hit and physically packing stuff in tight.
Yeah, maximizing the odds of hitting a layer and making that layer the best possible target.
But, and it's a huge but, as the sources really drive home, the overwhelming challenge is still just the fundamental physics. The weak force, the neutrino interaction probability is just so incredibly low.
Exactly. Even with the perfect material, that intrinsic probability per atom is the real bottleneck. It means you'd likely still need truly astronomical amounts of this stuff, an unbelievable number of layers to actually guarantee you'd catch a decent number of neutrinos.
And layered onto that are the just monumental technological hurdles, making the materials the atomic scale precision needed for potentially kilometers of this stuff, managing the forces, keeping it stable. It seems like engineering matter in a way we just can't conceive of right now.
That's really the core takeaway, I think. It's a concept that pushes the absolute bleeding edge of material science, of particle detection. It shows the kind of, well, almost fantastical thinking you need to even start tackling challenges like reliably detecting neutrinos.
It absolutely does. It kind of forces you to rethink what a detector could even be.
For sure. And, even if this specific method for neutrino detection turns out to be practically impossible, or at least centuries away, the thinking behind it, that's still incredibly valuable.
How so? Why should you, listening, care about this, seemingly impossible detector?
Well, because wrestling with how to interact with the universe's most elusive particles, how to manipulate matter at the most fundamental level, that kind of thinking forces us to imagine materials and engineering capabilities far beyond what we have today.
Right.
The core ideas here, the precision layering, the atomic level control, tailoring material properties, these could spark breakthroughs in completely different areas. Maybe not for neutrinos, but perhaps for detecting other different kinds of particles.
Okay.
Or maybe for creating novel materials with totally unforeseen properties for applications in, I don't know, computing or energy or something else entirely.
Huh. So the value isn't just the end goal, but the way it makes us think about manipulating matter.
Exactly. It's a powerful reminder, isn't it? Sometimes trying to solve the impossible problem with today's tools is precisely how you end up inventing tomorrow's tools, tomorrow's materials. So maybe the provocative thought is this: what other breakthroughs might be hiding in the challenge of trying to build something just to see the universe's ghosts?